that we are doing all those calculations for low pressure range to moderate pressure range. If you go to the high pressure range, how the VLE will work? VLE at high pressure range, and we know that basic principle of VLE is FIL equals to FIP. Okay, so FI is the fugacity of ion component liquid phase, and that you can write this as phi I xil into P, and similarly this phi IL, phi IB, YIB into P. XIL is don't put because X means liquid phase, Y means base vapor phase, you can write XIL. So P and P will be getting cancelled. So what will you get? You get Ki, which is Yi by Xi, which is phi IL equals to divided by phi IB. This is called as equilibrium constant. This is called as equilibrium constant. So whatever problem we did earlier, first set of problem we did for the ideal situation where the Gauss law actually is valid, activity coefficient is equals to 1. Then we have different activity coefficient models. We did the PXY, PXY. In fact, we have done Azure plot also. So now the question is if the solution liquid phase does not behave ideally, or the vapor phase doesn't behave ideally, it's at high pressure. I said 10 bar pressure. If it is more than 10 bar pressure, then we have to use this direct formula, and then you have to calculate the particular xi yi, so that this is actually valid. This formula is valid. So how to proceed? So you have particular xi initially, right? We have xi data. With that xi, we can or we have particular pressure of paper. So basically, you have the question is bubble pressure. About temperature. Temperature part you can do. That I will discuss the same way. Iteration process. Introduction method. Bubble pressure calculation. Temperature is given. The temperature is given, you can calculate SAT. P1 SAT, P2 SAT. By derivation. You calculate P1 SAT, P2 SAT. And then you calculate the Ki equilibrium constant. And if you calculate the Ki, you have Yi equals to Kx. Okay. And when you have this calculation, you can calculate after that you can calculate the fugacity coefficient. This fugacity coefficient has to be calculated based on the equation of state. So this has to be calculated by Payne-Robinson equation of state, or Swave-Redlich-Kwong, or Redlich-Kwong, or if you want you can do VDEUS. Whatever works, but I prefer Payne-Robinson equation of state. Okay, so you just follow the steps. What actually we are doing. We have temperature set up for bubble pressure calculation. The particular temperature you can calculate P1 SAT, P2 SAT, and after that P1 SAT, P2 SAT you can calculate. You can have the guess value of Ki. Initially you can have the guess value. From the guess value you can have actually Yi. You do all the calculations, check whether this is actually satisfied or not. If it is not satisfied, give the another guess. So try to see. Apply your basic knowledge how the algorithm will work, and this algorithm will be one of the questions in the exam. So how the algorithm will work? If I have high pressure, we have to solve for the fugacity. Remember that fugacity formula is same for the liquid and vapor phase. And why fugacity formula will be different? Fugacity values will be different because VL is not equal to VV. If phi IL will have VL, okay, phi IL will have VL. This will have dV, vapor phase, and with that will be different. And when we calculate the fugacity, you will see that FIL is not equal to FIB. There, because we don't have directly VL, we have the ZL. We could remember the formula has the Z. If you have Payne-Robinson equation of state fugacity formula, the big formula you have, ln phi I equals to Bi by B max into Z minus 1 minus ln Z minus B mix plus A mix by 2 root 2 B mix into B by B mix minus 2 summation Aij by A mix and whole multiplied by ln of Z plus B mix into 1 plus root 2 by Z plus minus B mix 1 minus root 2. So that means Z is required. Okay, and Z means what? PV by RT. PVL by RT is ZL. PVV by RT is ZB. Right? With that you can calculate phi I and phi IV, and once phi I and phi IV is calculated, we can see the values of the Ki. From that calculation, from the value of Ki, and if we have the value of Xi known, we can have Y. So this will be fed from the phi IL by phi IV. Okay. So, and we have to and when you do the calculation, you always check summation of y equals to 1 or not. If summation of y is not 1, then you have to do the integration process and solve it. And how to do the proper algorithm? If you want to write a computer program on this, because this requires computer programming. So this requires this can be done as computer simulation. This can be done by computer simulation. And if I ask you the exam, how to have an algorithm, what are the step-by-step procedure, you should be able to do it based on the so much things what we have learned so far. So we can do it, right? So please look to the books, give your ideas. I want you to have real thinking here. This requires a lot of thinking. I want you to have the thinking so that we can have the better perspective on the vapor liquid equilibrium for the high pressure. Okay, so with that I will end the vapor liquid equilibrium process and slowly move to chemical reaction equilibrium, the last part of the lecture of this thermodynamics course. Okay, so we'll start with chemical reaction equilibrium. So for chemical reaction equilibrium, it is actually multi-component substance. Reaction equilibrium is a multi-component substance. So it comes under multi-component single phase. I don't want to talk about multi-component multi-phase. It's out of syllabus or maybe the topic of advanced chemical thermodynamics. Much advanced, not advanced. Advanced is this course. It will be much advanced chemical thermodynamics. So you have a reaction A plus BB going to CC plus B. You can see there's multi-component. You can see this as multi-component. We will go multi-component single phase. Multi-component single phase reactive. Multi-component single phase reactive. If we consider initial moles of A, initial moles for A is Na0, B is Nb0, C is Nc0, D is Nd0. Initial moles of compound. When the reaction starts, the reaction starts after time t, or at time t, the number of moles becomes Na, this is Nb, this is Nc, this is Nd. Okay. If you look at the stoichiometry of this equation, which is A plus B by A, B, C by A, capital C, and D by A, capital D. It says that 1 mole of A reacts with small b by A moles of B. If 1 mole of A reacts, the small c by A moles of C are formed. If 1 mole of A reacts, small d by A moles are formed. Okay? So, what we can write from here, number of moles of B reacted, number of moles of B reacted divided by number of moles of A reacted, which is B by A by 1, which is B by A. And if you now look at number of moles of B reacted, it will be NB0 minus NB. Am I correct? NB0 minus NB. Na0 minus Na equals to B by A, which is NB0 minus NB by B equals to Na0 minus Na by A. Similarly, so this part is quite clear to all of you. Right? Similarly, number of moles of C produced. Number of moles of C produced by number of moles of A reactant, which is C by A, right? C by A by 1, and which is what to write in terms of number of moles? Madam, just one hand please. Yes, madam. NC not minus. Plus. What plus? NC not is there already. How much is production? NC minus NC naught divided by Na0 minus Na. That will be remain same. C by A, and we will get NC minus NC0 by C. Na minus Na0 minus A. So we can write the entire thing as, entire stuff as Na minus Na0 minus A equals to Nb minus Nb0 minus B, Nc minus Nc0 C, Nd minus Nd0 small d. Now you can see that, and this ratio, I write this as epsilon. What is this ratio called? Method of extent, extent of reaction. This is called as extent of reaction. And now if you see that extent of reaction, this A, B, C, D are called as a stoichiometric coefficient. And the reactant stoichiometric coefficient is coming with negative sign. Product stoichiometric coefficient is coming with the positive sign. Okay? So if you look at the extent of reaction, the denominator part will be having the stoichiometric coefficient, the reactant stoichiometric coefficient will be negative, and product will be positive. That's the convention. And it's coming, that convention is coming from this relationship. Okay? So, thus, this reaction can be expressed, any reaction can be expressed in terms of the stoichiometric tensor. Have you heard about the stoichiometric tensor? So, any reaction can be expressed as a stoichiometric tensor. What is tensor? Vector has one direction, tensor has two directions. Tensor has two directions. So that gives a flavor. People talk about n-dimensional vector space. You have done in mathematical methods in chemical engineering. Sometimes people will say, what is n-dimensional chemical n-dimensional space? How can you visualize? Maximum you can visualize three-dimensional space. Velocity components, u, v, w, or there are different cases you can actually have three components. But more than three, maximum you can say, okay, time is also one coordinate. Astrophysics talks about the fourth dimension. 5 dimension, 6 dimension, 7 dimension, 10 dimension. Who are dealing with? Physicists will say, no, we don't know. Only the people who can say, we talk about the, all these 10 dimension, 12 dimension are the chemical engineers. So chemical engineers are the only people who are talking about the real n-dimensional vector space. And if we talk about the coordinate axis, in chemical reaction engineering, the classic subject, each coordinate axis can be represented by independent chemical species. And we have seen earlier in mathematical methods in chemical engineering how to find out number of independent chemical reactions. How to find out number of independent chemical reactions? Any idea? If I have say 15 reactions, out of that maybe 10 reactions are independent, 5 are dependent. How to find out number of independent chemical reactions? How to find out number of independent chemical reactions? Row echelon form. So this reaction can be expressed as or you can say I, whatever. This I denotes species, J denotes reaction number. Okay, so that's why this term is known as a stoichiometric tensor, has two indices. A stoichiometric tensor has two indices. Okay, one is species, that means I have only one reaction. So my first reaction, first species is A. Please don't get confused with this A. Okay, don't get confused with this A. What is that? AI. A1 equals to A, A2 equals to B, A3 equals to C, A4 equals to D. One is clear for AIs? Okay. So now, this new IJ talks about the stoichiometric coefficient of jth reaction of ith species. I have my J is 1. There is only one reaction here. Okay. So what will be my first new 1 equals to minus A. New 2 equals to minus B. New 3 equals to plus C. New 4 equals to plus D. So what we say that this reaction can be expressed as an algebraic equation. The algebraic equation is CC plus DD minus AA minus BB equals to 0. This is not correct for chemical reaction, chemical engineers. For mathematician, that's the correct expression. Why it is correct expression? Because we will have all the time balance, proper balance. If you have the proper stoichiometric balance, we can write this stoichiometric equation as an algebraic equation. Okay. So the convention is the stoichiometric coefficient will have positive sign or negative sign. When it will have positive sign, when AI denotes the product, when AI denotes the reactant, the stoichiometric coefficient will be negative. When AI denotes the product, the stoichiometric coefficient is positive. When AI denotes the reactant, the stoichiometric coefficient is negative. Okay, so if I have 1000 chemical reactions, I can write the set of algebraic equations. I can have, so my algebraic equation is given by right? Am I correct? This will be a matrix. This will be a matrix. It will have new 1 new 1 2. You can say new 2 whatever. And then again you have new 2 new 1 2 new 2 2, then you have new 1 3 new 2 3 and so on. A is the species. Okay. Most of the cases this is a non-square matrix. People ask, where is the example of non-square matrix? You could have asked this question in mathematics and chemical engineering. Non-square matrix, people will say there is no use non-square matrix, we don't know. Non-square matrix, again chemical reaction engineering. Chemical reaction engineering, such a subject, is very rich in mathematics. It's very rich in mathematics. If you want to do marks mathematics, it is the only subject chemical reaction engineering. There is a challenge of mathematics, and where you can do is a place for the world of vectors and tensors. In fact, anybody can teach the entire chemical reaction engineering with vectors and tensors only. In fact, with tensors. So tensor is ideal word in chemical reaction engineering. Okay, so this is a classic example of non-square matrix. Most of the case, this will be non-square. So stoichiometric tensor is the classic example of non-square matrix. You cannot have any other. So please write down. If you just look at me, don't look at me. Whatever points I'm stressing, giving the stress, we have to just write down. So then do the echelon plus echelon form here, and the echelon form we can easily find out. In the echelon form we can easily find out how many how many non-zero rows in the echelon form. So rank of the matrix is defined as number of non-zero rows in the row echelon form. That's what we know. And number of non-zero rows will tell you how many dependent chemical reactions. So that's why it is better to have this type of format of any. So world of chemical reaction engineering can be represented by this question. Okay. So I don't want to talk much on the chemical reactions, but I would like to note at this point when chemical engineering started, it was started with the paint industry, soap industry, and so on, and it was actually applied chemistry. So there was not much. In fact, unless Professor Neil Amundsen, who did BSc in mathematics in 1937, and he did BSc from University of Minnesota, which is number 1 in chemical engineering, but he did BSc in mathematics. He was talking to his friends, and he found there are a lot of challenges in chemical engineering. So he did masters and PhD in chemical engineering, and because of that, and where this chemical reaction engineering species, they talk in terms of the functional space. People talk about Hilbert space and all, and he's the first person who found chemical engineering has so much of mathematics potential. So then he guided so many people as for PhD students like Ramakrishna and all these people, and you have the books by Lapidus, Spindler, all these books are there. And here's the book by Aris Amundsen. You might have heard those kind of books. And I had the fortune to work with him when I was doing my second postdoctoral fellowship, fellow in University of Houston, Texas. He was my postdoctoral advisor, and at the time he was 88 years old. I'm so sad, just last year he died. And we are working, and although he was a chemical engineer, was a professor, he died as a professor of mathematics, and I did my second postdoc in mathematics department. What actually happens, he wrote a couple of books of mathematics, and when I was coming back to India, he gave his own book. One copy was left with him. He said, I don't know, they will teach to chemical engineering students. You go back to India and teach from my book. So that's the legendary of chemical engineering, who was the first chemical engineering mathematician in the world today. And I had the fortune to work with him as my postdoc, for a postdoctoral advisor. And because so much mathematics we do, we teach mathematical and chemical engineering, we teach so much of mathematics and thermodynamics because of him. If you wouldn't have been born, I think chemical engineering would have been confined with the soap industry and all the industries. In fact, I wouldn't be working so much in math in chemical engineering because of him. So I wanted to make that one. Okay, so let me talk about the method of the extent of the reaction. Let's look at that part. So, generalized perspective of the extent of reaction, what we can write as NaI, T minus NaI0 by mu ij, which is epsilon. Epsilon naught, you can say J. Jth reaction. In this chemical reaction engineering, chemical reaction equilibrium, I do not want to talk about the multiple reactions. Mostly I will be confining myself with a single reaction. Okay, so this is the generalized definition of the extent of reaction. This for time t, this for time 0, and for jth reaction. So this definition is valid for multiple reaction. So the generalized definition of the extent of reaction. The generalized definition of the extent of reaction. So this also you can write as dni by mu I equals to epsilon for single reaction. dni by gamma is equals to epsilon. So this relationship we will be using quite often. dni by gamma equals to epsilon, but dni is number of moles consumed or produced. Gamma is the stoichiometric coefficient with the proper sign, and epsilon is the extent of reaction. Right? So now we are saying that multi-component mixture. For multi-component mixture, what should I write? The thermodynamics dg equals to minus sdt, then plus vdp, then plus mu I mix summation. We are not saying summation. Summation I equals to 1 to c mu I mix dni. Now, if the reaction occurs at constant temperature, so this is the multi-component mixture single phase. Gives energy. The reaction occurs at constant temperature and pressure. The reaction occurs at constant temperature and pressure. We have dg equals to 0 at equilibrium. That's a very important part. At equilibrium, at constant temperature and pressure, this guy will go and dg equals to 0 at equilibrium. At equilibrium. At equilibrium, this is equals to 0. It means that summation I equals to 1 to c. So if you want to know why it is 0, because you have this kind of stuff, right? So derivative of the thing is so at the equilibrium, at this point delta g equals to 0. So if dg equals to 0, that means that that's of course temperature and pressure are same, okay, at equilibrium. And mu I mix dni equals to 0. Mu I mix dni equals to 0. So at dg equals to 0 at constant temperature pressure. So mu I mix dni equals to 0 implies that system is at constant temperature and pressure and also at equilibrium. System is constant temperature and pressure at equilibrium. This is the equilibrium and you have the constant temperature and pressure. Okay, so system can be system has to be equilibrium at constant pressure because we have the conditions like T1 equals to T2, P1 equals to P2, and we have mu1 equals to mu2. There's another way to explain. Okay, and that's it. So that's the way we can explain various ways that how it has to be at equilibrium. And what you can write, summation I equals to 1 to c mu I. What is dni? Epsilon into gamma, right? Then what you are getting, summation I equals to 1 to c mu I mix gamma I equals to 0. So you got at equilibrium summation mu I mix gamma I equals to 0. So another relationship we got. So first relationship is this one. Second relationship is summation mu I mix gamma equals to 0. So we have to do more on that. We have to get some more insight on that. What we are supposed to do that reaction equilibrium we have to find out, and for that purpose we need to express mu I mix, because mu I mix we don't know how to estimate mu I mix. That's a honest challenge. Chemical potential is not estimate. In our methods for multi-component system we have done for the fugacities. For the pure substance we have the pure component fugacity. Multi-component substance we have multi-component fugacity. Here we introduce something called activities. Not activity but activities. Okay? So we'll talk about something called activity of species. We'll talk something on activity of species. AIM, which is exponential mu I m minus mu I ss by RT. It is analogous to fugacity, a multi-component fugacity, but not exactly, because this denotes as steady state, standard state. The standard state is a very interesting part in chemical reaction equilibrium. Based on the standard state, your expression will be changed, but whatever you do, your measurement value will not get affected much on the standard state. So SS refer to the standard state, and this may be defined in 2S. 2S, you can do SS. Number 1, ideal gas of component I, which is the temperature T and pressure PSS. So ideal gas of component I at temperature T and pressure PSS, which is arbitrarily chosen. So we can have ideal gas situation at temperature T and pressure PSS. So in that case, your mu ISS is nothing but mu I Ig T PSS. One step, one possibility. Second possibility is pure component I at temperature T and pressure PSS arbitrarily chosen. That is mu I SS equals to mu I TPSS. Difference is ideal gas, one is just pure component. One is ideal gas, one is just pure component. So two standard state one can actually have. Based on that, the activity of this species will change, and this expression, which is our main expression for the equilibrium, which is summation mu I mix I gamma I, and that will give a lot of interesting episode that depends on the standard state. So let's proceed further. What you can do is so much definitions. We have discussed more definitions in this chemical reaction equilibrium. So first we'll be talking about the activities measurements. So we'll do that first with the first assumption of SS, ideal gas. Then we'll be going to the pure component. So we have the activity formula, which is AIM, which is exponential of mu I M mixture minus mu I SS by RT, and we can write this as mu I M equals to mu I SS plus RT ln AIM. Mixture M is mixture. Now we can apply your basic knowledge. For chemical reaction equilibrium, at equilibrium, just now we have learned summation I equals to 1 to C mu I M gamma I equals to 0. Just now we have learned. So this mu I M can be substituted here. Okay. If you do that, summation I equals to 1 to C mu I SS plus RT ln AIM gamma I equals to 0. What you will get? If you do the things properly, we can have summation and right side gamma I mu I SS. What will be the left hand side? One term I am taking it out. Very simple. Mu I SS gamma I am taking it out. Right hand side. Left hand side.
RT summation summation I equal to 1 to C RT ln AIN gamma.
You can simplify much. RT. If I say ln, what you can simplify? ln A plus ln B is ln AB. ln A1 plus ln A2 plus ln AN. What should you write? In initial notation, pi I equals to 1 to n AI. You didn't know this? Okay. Yes, so what will happen here? And now, if you have ln A1, alpha 1, alpha 2, alpha 3, we can write this as alpha I. Correct? Yes or no? So, now tell me what's the answer. Everything you will have. RTLN. RTLN, what is the answer? Yes. Yes, tell me. RTLN pi equals to 1 to C. Okay, very interesting. So far nothing I have done with steady state assumptions. I am just doing more generalized. So this is termed as activity based equilibrium constant. This is known as activity based equilibrium constant. If you remember our main equation A plus BB CC plus DB, you might have done earlier KP KC, right? Last Atelier principle. See, so many things you could remember. Last Atelier principle in chemistry. How to define KC? Concentration of C to the power C into concentration of D to the power D divided by concentration of A to the power A, concentration of D to the power D. Kp is in terms of partial pressure. And based on that, if the number of moles are not the same, both sides, it don't balance, so Kp cannot be equal to Kc. That can be proved. And there is a relationship between Kp and Kc, which can be proved. Okay? Okay, that's fine. So, what is this activity coefficient base? This gamma. So, these are your gamma. This is gamma 1, gamma 2, gamma 3, and gamma 4. Now, if you look at this Ka, what I am saying, what it says, this entire thing is to the power gamma I. That means what should I write for our case? Ka equals to, this gamma is positive for the product, negative for the reactant. So reactant part will come into denominator, right? So it will be coming as AIM to the power, sorry, AC to the power C, A B mixture to the power D, it should be capital C, capital D, capital A B mixture small. If you look at our Kc expression, this A should be replaced by its concentration. Capital K is A is replaced by partial pressure. So that's why this definition is valid definition. Equilibrium constant based on activity coefficient. Based on activity. Because we have the equilibrium constant based on concentration, based on partial pressure. The same kind of definition is valid here. Okay? So we have learned Kp, we have learned Kc, we have learned Ka. Okay? Correct? And what we actually did, and how did you get the Kc part? Because when you have the reversible reaction at equilibrium, we say that forward reaction rate equals the backward reaction rate, and then based on the reaction rate, we can write. So if you have the main reaction, you can see that the backward reaction is K into C to the power gamma 3 into D to the power gamma 4 equals to that, and with that K1 by K2 is Kc. Okay, so much background is required with chemistry. If you have all this background, then you can really appreciate. So Kp, Kc, K, all formulas are actually cleared by now. Now I think I can slowly go for this treatment after this small background. So we have got the Ka. Now we'll see that how that activities. So basically this definition of activities will be based on how you select the standard state. So definition of activities. So this will actually change. Of course, this will be changing based on the definition of standard state. So we'll go for the ideal gas definition first time. First time standard state. First time standard state. Ideal gas state. Ideal gas state. Where we write mu I SS equals to mu I Ig Tp SS. And here we found the final relationship, which is ln Ka equals to minus 1 by RT summation I equals to 1 to C mu I So what it says that ln K will be changed based on SS, how you select SS. Okay, so many things we are seeing that this SS is playing critical role. Very important. And how to evaluate. So mu I SS equals to mu I Tp SS and ln K equals to minus 1 by RT summation I equals to 1 to C gamma I mu I SS. You can also write this as, for our case, minus 1 by RT summation I equals to 1 to C mu I Ig, or you can write this as summation I equals to 1 to C gamma I Gi Ig Tp SS. Correct? Now we look at activities AIM based on the first definition. Based on the first definition, what we can write? This has mu IM and mu IG. Okay? I have done this kind of derivation earlier. Okay? How to start? The numerator part. Mu I mixture. What kind of definitions you can actually get? If you have mu I IgM, we can have velocity. So we can have mu IM minus mu I IgM plus mu I IgM minus mu I Ig. So this mu I IgM is Tp x bar, and this is Tp SS. Exponential, so first term will be exponential mu IM minus mu IgM by RT. Next, what is the remaining term? What is the remaining term? Remaining term, is it the same? We don't have any other term? You are saying is this correct? This step is correct? Then you are saying Fi something. I am not saying that. I am saying is this step correct or some other term will be within this step. So I am doing simple mathematics. E to the power A plus B equal to e to the power A to the power B. laws of indices. I don't know how to do theoretical work again because simple mathematics you are not able to tell that. What is the next step? Exponential mu y igm ppx bar minus mu y ig ppss how we define fi? Fi by b equals to phi I, which is equals to exponential mu I minus igm by RT. Remember that this mu I igm is denoting temperature, pressure, x bar. This is the pressure. But our pressure is PSS. This is what? This will give what definition? First term. First term will have some definition. What is that? This will be PXI. Sorry. This will give, first term will be what? First term will be what? You have given the board and you cannot even reproduce from the board. Phi I. Fi by PXI. Second term. This for TPX bar, this is for TPSS. Any formula is there? Mu IIGM, mu IG plus, look at the notes. RT ln xi? Yes or no? So what did you get? Mu I ig, what did you get? Exponential mu I ig TP plus RT ln xi minus mu I ig TPSS by RT. Am I correct? Yes. Fi by PXI already there. This term you have to take it out. What do you get? This term I want to take out. E to the power ln x is x. Next, you have exponential of mu I ig TP minus mu I ig TPSS by RT. This xi and xi is getting cancelled. You are getting here Fi by P. Fi mixture by P. You can have mixture, no problem. What will you get? This term. Change in pressure is there, temperature is same. What will you get?